Hello, everybody, and welcome back to our program, applying the 7 steps of data analysis to produce a quantitative research study. I'm William Bannon of Stats Whisperer, back with you. Okay, in this presentation, we are going to review Step 6 multivariate analysis for Sample Study 1. Specifically, we're going to be using multiple linear regression to examine the joint effects of several predictors, which are independent and covariate variables, upon our continuous dependent variable happiness. Okay, through this analysis, we will determine the strongest predictor of happiness, as well as determine our final levels of statistical significance for each predictor. That meaning that sometimes when you do a regression analysis, predictors that were significant at the bivariate level are no longer significant. So that's what we'll find out. And again, in our 7 steps of data analysis, drawing here, we have 6, right? We are way down there at multivariate analysis, step 6. You'll see you are here right there. Okay, so if we're looking at our parallel between data analysis and data analysis, right? So for the bachelorette, step 6 in data analysis is where the bachelorette considers among all the bachelors she has a significant one-on-one relationship with, which one does she have the strongest relationship with? And that is the bachelor who receives the rose indicating the strongest relationship. Now in data analysis, we don't have any roses, but the process and what's indicated are quite the same, right? So in data analysis, what we're looking at is we're taking all the predictors that have a significant one-on-one relationship with the dependent variable happiness, remember? And that was identified in bivariate analysis. Then, through a regression model, we're going to determine which of these predictors, education level, income level, and living with a dog or a cat, has the strongest impact on the dependent variable happiness. In other words, we're determining the strongest relationship between the predictor of happiness with the strongest impact on happiness, as well as determining the strongest relationship between the bachelorette and the bachelor with the strongest relationship. All right, so if we want to break down our terms, we see for multivariate analysis, multi means many, and var means variable. So what we're doing here is we are conducting an analysis between many variables, specifically many predictor variables, that being our covariate and independent variables, with the dependent variable. So let's recall our study map for sample study 1. Right on the left-hand side, we see our predictors, the covariate variables 1 and 2, education and income level. And then on the bottom, we see our independent variable, do you live with a dog or a cat? And these predictors are predicting, on the right, our dependent variable happiness. Now, recall, in bivariate analysis, we did 3 separate bivariate tests, right, for that step. We did a test for education level and happiness. We did a test of association for income level and happiness. And we did a test of association for do you live with a dog or cat and happiness. So there was 3 separate tests. However, in step 6, multivariate analysis, we are going to do 1 test, the multiple linear regression specifically. So we are going to regress all 3 predictors in 1 test at the same time upon the dependent variable happiness. So multivariate analysis is going to answer some big questions, right? First, like we said in our intro, it's going to tell us what's the final statistical significance between each covariate variable and independent variable with the dependent variable happiness. And end, when the effects of all are considered, which is still significantly related to happiness. And then two, it's also going to tell us which predictor has the strongest relationship with the dependent variable happiness. So, to perform multivariate analysis for sample study 1, we are going to need the multivariate test key, right? So you could see in our program, we have the univariate test key, we have the bivariate test key, and now we have the multivariate test key. And we'll use the multivariate test key to figure out the tests we need to do for sample study 1. So let's continue. So at step 6 multivariate analysis, you may wonder, how many tests do you need, right? And essentially, there are 3 tests we need to consider. The first one, linear regression, 2, binary logistic regression, and then 3, multinomial logistic regression. Now by the asterisks, keep in mind, this is because we're doing a cross-sectional analysis, meaning there's one time point, right? So there's one dependent variable measurement, right? If we were doing a longitudinal study, we would use different multivariate tests. But for our cross-sectional study, essentially these 3 are what we need. So again, the key to choosing the correct multivariate test is to look at the structure of the dependent variable. So again, we'll consider 3 variable structures. The first one's continuous, such as our happiness measured on a continuous scale of 1 to 5. 2, a categorical variable with 2 categories, such as happiness, yes, no. And 3, a categorical variable with 3 or more categories, such as happiness, yes, no, or somewhat, right? In between yes and no. So here's our multivariate test key. We see in the left-hand column the dependent variable listed. We have the 3 structures we mentioned, continuous, and then the 2 forms of categorical. And then to the right, we have each of the regression tests we mentioned. So if we plug in our samples of structure, this is what we have. So when the dependent variable is happiness, measured on a continuous scale of 1 to 5, the regression test to use is linear. Okay, so that's the regression test we need. Now, when you do a linear regression and it has more than one predictor, it's referred to as multiple linear regression, which is what we'll be calling our regression because it has more than one predictor. So what's being answered here in linear regression? The question, does a significant linear relationship exist between the dependent variable, which is continuous, and the predictor variable, which could be the covariate variable or independent variable, right? And while controlling for other significant influences on the dependent variable, right? That's the big benefit of our multiple regression here, is we can control for other influences. Now, recall the linear relationship, right? So let's say we're looking at, does a significant linear relationship exist between happiness and the predictor income level, the covariate variable, okay? So the linear relationship, if you recall, right, we mentioned this earlier in our checks of data integrity under test assumptions, right? What a linear relationship is, right? So that means as one continuous variable increases, the second continuous variable either increases or decreases at a significant level. In our example here, we see on the bottom, the x-axis, as happiness goes from 1, 2, 3, 4, 5, increasing, right? The scores for income. So suppose this is hundreds of thousands or tens of thousands. It increases 1, 2, 3, 4, 5 as well, meaning you look at the intersections. So the score for happiness at 1 is about the same as the score for income at 1. And the score for happiness at 2, going straight up, 2, is about the same for income at 2. Likewise, a score of happiness at 3, if you go straight up, is about a score for income at 3. And the same with 4. A score of happiness at 4, high score, goes up to here, then across, is also a high score for income. And then 5, the highest score for happiness, is also the highest score for income. So that means as the happiness scores increase, the income scores also increase. And they form this diagonal line. So you can draw this line, this diagonal line, almost through the points, right? These are the points at which each, right, correlation meet, right? So you could draw this line. This is the regression line, right? So linear regression. This is the line that regresses. So if we regress and go backwards, we get to 5 and 5, 4 and 4, 3 and 3, 2 and 2, 1 and 1. Right, those intersections. So that's what we're looking at with our linear regression. So now, in regression, remember, right, we can't have categorical variables with more than 2 categories. So when using a categorical predictor, right, with more than 2 categories, each category must be dummy coded, right, made into a yes/no variable for use in the regression model, right? So dummy coding is a form of recoding, right? Remember when we did our data entry week and we did our recoding, our reverse coding? Well, that same recoding is done, right? See pages 204 to 212, right? That same recoding is done to dummy code our variables, right? So dummy coding turns the single categorical variable into yes/no, a series of yes/no variables. For example, the variable education level, right, is one variable with 3 possible categorical responses, being high school GED, college or graduate school. So the original variable education level, the study participant would choose one of these 3 categories. However, through dummy coding, it now becomes, right, 3 dichotomous. Remember dichotomous, 2 categories, yes, no. Doesn't have to be yes, no, but dichotomous means 2 categories. In this case, it is yes, no. So education level becomes 3 dichotomous yes, no variables. Variable 1, education level high school GED, yes, no. Variable 2, education level college, yes, no. And variable 3, education level graduate school, yes, you guessed it, yes, no, right? Now the key in the multiple linear regression, as well as the other forms of regression, is you need to leave out one group, and that becomes the reference group, right? And the findings from the other groups left in are in the context of the reference group, right? So choosing the reference group, there's a few ways of doing it. One might be the group that you're most interested in, you might leave out as the reference group. So suppose high school GED was our independent variable, and who we were interested in were the study participants with a high school GED level of education. Well, we might leave out the variable 1, right, education level high school GED, and then in the regression model, the findings for the other 2 variables, education level college and graduate school, refer to high school GED. You'll see this in our model. It'll be much clearer. Okay, now also keep in mind, so we'll go through that in the model. So it'll be really clear once we do it. Remember, when we do things, they become clear. When we talk about them, they're pretty clear, right? But they're extremely clear when we do them. Okay, so remember, if we have a categorical variable that's already dichotomous, such as do you live with a cat or a dog, and the response is dichotomous, two categories of cat or dog, we don't need to dummy code anything because it's already dichotomous. Okay, so here is our path for our regression model, right? Linear regression in SPSS. So why don't we just do that live right now? So here we are in SPSS. We go to Analyze. Then we go to Regression, right? It makes a lot of sense. And then Linear. All right. So now we look for, see, dependent. That's the dependent variable in the top box on the right. So that's happiness. So from the left, we highlight happiness, put it up to the right. Now, here's what I was talking about when I say we have to leave out one of the dummy coded education levels, right? So education level high school, we won't put in the regression model, right? That'll become the reference group. So it'll essentially become an analysis saying if college and graduate school are significantly more happy than the reference group high school. So that's what's done in a regression model. You need to specify a reference group. So you put in education level college, education level graduate school, right? Then the next covariate, income level, we put in. And then we put in our independent variable, do you live with a dog or a cat? And there we go. There's our dependent variable and our predictors. Now we also might choose to go under statistics, right? And click collinearity diagnostics. That's what gives us our values for multicollinearity. Remember the intercorrelation between the predictors, which is one of the test assumptions. And continue. Then under plots, we might decide to go in there, and in X and Y, we might put Z pred by Z resid and continue, because remember, that's what gives us that figure with all the dots that, if they're evenly dispersed, indicates an acceptable level of homoscedasticity and linearity. Recall that from our checks of data integrity. Okay? Then, of course, we're going to paste. So we paste, right? And then, right, in our syntax, there it is, our regression model, right? And then we would just click the big green button, and then it would run. Now, of course, we already have our SPSS output, right, in our slides. So let's go back to our slides. Okay, here we go. Now, the first thing you'll notice, right, as per our instructions, in the regression output is a table about halfway down in the output labeled ANOVA. The final column in the ANOVA table indicates if the model is statistically significant. And we see ours is here, right, because it's far below 0.05, it's 0.000. Now, if the model's not statistically significant, nothing in the model is considered credible. So you can stop looking at the regression model right there. Because if it's not 0.05 or below, we consider that all the findings in the model are just by chance, right? So we can't take them seriously. Okay, next, a couple of boxes down, you will see this in the printout, right? So these are the coefficients. So these are telling us the values for the individual predictors of happiness, the dependent variable. So second, right, look at the statistical significance of the predictors, because every now and then you'll get a significant model, right? The last slide, but none of the predictors significantly predict the dependent variable. So we have to check and make sure they do, right? So we see here the significance level for all the predictors is statistically significant, right? So that's fine. So if we're looking at our dimensions of a relationship, right? This is the first one, right? This is significance. So all these relationships are statistically significant. So we will look on at all of them, right? So the next dimension, right, is our directionality, okay? So we know that they're significant, but are they significantly positive, negative, right? What's the story? So when we look at college and graduate school and we see a significant, that's significant in terms of the reference group. So what it's saying is, so there's no minus signs here. So that's a positive, meaning more relationship. So those with an education level of college have significantly, right, more, right, positive direction, more happiness in reference to the reference group, those with a high school level education. And you'll recall in our ANOVA, that's also what it said, right? So the bivariate level test like the ANOVA, it's also being reflected at this multivariate level. Then also education level graduate school, right? Positive, no minus, and significant. So those that have an education level of graduate school have a significantly higher level of happiness in reference to the reference group, those with the education of high school GED. All right. Then income level, right? So there's no minus, so it's significant and positive. So it's a significant positive association between income level and level of happiness, meaning as your income level rises, so does your level of happiness. Now, the next predictor, you have to consider the coding, right? So do you live with a dog or cat, the independent variable? Now recall, dog is coded as 1 and cat is coded as 2. So as you go from dog to cat, right, there's a minus, which means a negative relationship. So as the independent variable increases from 1 to 2, the dependent variable decreases, right, because it's a negative relationship with a minus. So the dependent variable decreases. So there's a significant relationship between do you live with a dog or a cat and happiness, right? Where those that live with a cat have significantly less indicated by the minus sign, less happiness. Okay, then the standardized coefficients beta, otherwise known as the standardized beta, that's telling us what the strongest predictor in the model is, right? So the higher the number, right, it goes up to 1.0, 0 to 1.0, the higher the number, the stronger the predictor. And we see the strongest predictor is the second up from the bottom, 0.386, which is income level. So income here is the strongest predictor of happiness, the dependent variable. But we see that it's not lopsided. They're all around that, 0.30 level, right? So income's closer to 0.40, but do you live with a dog or a cat is about 0.31, right? And the education levels are around there too, around that 0.30 level. So they're all relative in their predictive strength. Now, fifth, we can look at, and we looked at this before to see the directionality, but we could look at the unstandardized beta to see the degree of change in the dependent variable per unit change in the independent variable, or one of the covariates. But here we're looking at the independent variable. So what the unstandardized beta says is, as the independent variable or predictor increases in units, for example, from 1 to 2 to 3 to 4, what's the change in the dependent variable, right? So for living with a dog or a cat only has 1 point unit change. It goes from 1 to 2, right? So we see the unstandardized beta is negative 0.461. So that means as the independent variable goes from 1 to 2, the dependent variable score decreases, right? Negative, it decreases 0.461. So that's what that indicates, right? So that's about half a point, which is large because the dependent variable happiness only goes 4 points, 1 to 5, right? And so of those 4 points, it's saying that if you live with a cat instead of a dog, you have almost half a point would be 0.5, a half a point decrease in your happiness score. So that's what that indicates. All right, now the R squared, this is an important effect size also for a multiple linear regression. This indicates what's the degree of variance explained in the dependent variable by our predictors, right? So don't forget, variance just means varying up and down. So happiness scores in the dependent variable go up and down from 1 to 5. So we're just trying to explain what makes those scores vary to 1 to 5, right? We could explain a little bit of that variance or a great deal, right? So what this is saying is the R squared is 0.489, which is almost 50%. So what that indicates is almost 50% of the variance in happiness scores, right? And if you look at the effect size for the R squared, that's huge, right? Almost 50% of the variance in happiness scores are explained by our 3 predictor variables. And the adjusted R squared is our way of saying, look, we know out in the, right, so this is our sample that this R squared is from, but out in the population, the study population is probably not exactly what the R squared is for our sample. So the adjusted R squared is our projection of what that variance might be, the R squared in the population. So the closer the adjusted R squared and R squared, the more stable the finding. So here the adjusted R squared is 0.43, which is pretty close to 0.49. So it looks like a rather stable R squared. And then we want to look at the effect size. So the way we did our effect size, as shown on page 219 of our textbook, is we did an ANCOVA, right? Because that produces the partial eta squared, right? So we loaded up all our variables into an ANCOVA, which is very much like a multiple linear regression, right? And it's analysis of covariance, right? So we have our independent variable and our covariates covarying being controlled for. So our effect size for the partial eta squared was 0.092, which is a medium to large effect size. So we could say living with a dog or a cat has a medium to large effect size on your level of happiness. All right, so if we sum it all up, right, we have in our yellow boxes to the left our three relationship dimensions. Okay, so the multivariate model indicated while controlling for education and income level, living with a dog or cat is related to happiness where those living with a dog, so dimension 2, D2, that's our directionality, living with a dog are significantly happier than those living with a cat. Then dimension 1 at a statistically significant level, right? And then D3, dimension 3, the magnitude, with a medium to large effect size. So our big accomplishment, we have used statistical analysis to identify the significant influences on the dependent variable happiness in bivariate analysis. Then, too, we use multivariate analysis to control for those significant influences of the covariate variables while noting the independent-dependent variable relationship of interest, right? It's all very solid. Then 3, we've identified at the multivariate level if there is a statistically significant independent-dependent variable relationship and that directionality, right? As well as the effect size of those relationships. All right, next class, we're going to do step 6 multivariate analysis for sample study 2, where we'll use binary logistic regression to examine the joint effects of the predictors, right, on the categorical dependent variable. We're going to determine the strongest predictor and the final statistical significance. All right, which will be, again, next week's completing step 6 multivariate analysis. All right, thank you, and I will see you at the next session.